In this presentation, we will work through finding the zeros of a particular fifth degree polynomial, and while we're at it, we'll find bounds on the set of zeros for a polynomial. We'll work through the details of trying to compute exactly the zeros of the polynomial, and these techniques, that are over 3 centuries old, are now aided by tools such as graphing calculators. Let's work through an example in detail. Suppose we wish to factor completely this fifth degree polynomial. We might first create a test set of rational roots to try. Here the constant term is minus 30, which has factors 1, 2, 3, 5, 6, 10, 15, and 30, quite a list. And the leading coefficient is 2. That has factors 1 and 2, and so those are possible denominators for our rational roots. So by the rational root test, here's our list of possible rational numbers to try. All of these numbers have numerators dividing 30 and denominators dividing 2. Now this is a large set. Alright, so we're going to factor this polynomial with this we have this large rational test set. So let's just jump in. Let's begin by trying an easy number from this list. We're going to try whole numbers first, and in fact let's try dividing by x minus 1 using synthetic division where c is 1. So we're going to see if c equals 1 is a rational root. There's my synthetic division. You could work this out on your own. And when you plug in a 1, according to the remainder theorem, you get minus 36. So f of 1 is minus 36. So x equals 1 is certainly not a 0. This might be discouraging. There are a lot more things to try. But notice that doing synthetic division with c equals 1 was awfully easy. Alright, so we're trying to factor this polynomial. Let's try something else. We already tried c equals 1 and got that f of 1 was minus 36. So let's try the integer 2. We'll see if 2 is a root. There's my synthetic division. If I look far to the right at that 90, I notice that f of 2 is 90, and so x equals 2 is not a 0. Darn. But notice two things here. Here the remainder was positive, f of 2 is positive 90. In our earlier work we discovered that f of 1 is negative 36. And so, by the intermediate value theorem, the graph of the function f of x crosses the x-axis somewhere between 1 and 2. When we plugged in 1 we got a negative number, we plugged in 2 got a positive number, so the graph must cross the x-axis somewhere between those. Since f1 is negative and f2 is positive, there's a 0 somewhere between 1 and 2. That's important information, and let's remember that for later. Meanwhile, notice what happened. We tried f of 1 and got minus 36. We tried f of 2, got this synthetic division, and discovered that f of 2 was 90. And we concluded there's a 0 between 1 and 2. But if you look at the bottom row of our synthetic division here with c equals 2, we get all positive numbers. We can conclude from our understanding of synthetic division that if we were to try a larger positive number c greater than 2, something like 5/2 or 3 or 5 or 6 from our set, then the numbers on the bottom row would get larger still. Notice that the numbers in the middle row, like 4, 2, 32, 94, 120, came from multiplying bottom row numbers by 2. If instead we had a larger number, c, then those numbers would get bigger still, and when we added, the positive row would get bigger still. So there's no chance of a 0 bigger than 2. Since 2 gives a bottom row of all positive numbers, anything else larger than 2 would give a bottom row of even bigger positive numbers. So we've found an upper bound on the zeros of our function. Alright, we're factoring this. We tried c equals 2. We got that. We now know not to try anything bigger than 2 because that bottom row is all positive. Since multiplying the middle row by a bigger number c would give us a number larger than they are now, so there's no chance of a 0 to the right of 2. This is an upper bound for polynomial zeros. If, upon synthetic division with a positive value c, the bottom row in our computation consists of all positive numbers or 0, then c is an upper bound for the zeros. We don't look further to the right on the x-axis for other zeros. The graph will not cross the x-axis again to the right. Alright, so we have this rational test set. We found that 2 didn't work. but it's an upper bound, so that rules out lots of bigger numbers like 5 halves, 3, 5, 6, or whatever. We've reduced the size of our test set. We don't need to try any of these. All right, we still need to factor this thing, and we haven't found any zeros yet, but we did notice that there needs to be a 0 between 1 and 2. So let's try 3 halves. If I do the synthetic division with 3 halves, always multiplying by 3 halves, I pull down the 2, multiply by 3 halves and get 3, and add and so on, we get this. Notice the remainder far to the right, at the bottom right, it's 0. So x equals 3 halves is a root of f of x, and in fact f of x factors as, reading off from the bottom row, it factors as x minus 3 halves times 2x to the fourth plus 0x cubed plus 14x squared plus 36x plus 20. Notice that we've found this linear factor x minus 3 halves, and then what's left as a factor involves multiples of 2. We could factor a 2 out of the right-hand side from the 2, 14, 36, and 20, multiply it into the linear term x minus 3 halves, and rewrite this as factoring my polynomial of degree 5 into 2x minus 3 times the fourth degree polynomial x to the fourth plus 7x squared plus 18x plus 10. All right, so we found this factoring. We need more roots. But since we factored out a linear term, let's focus on this fourth degree polynomial that's left over. There's an important principle here. Once we've found a factor, concentrate on the quotient that remains. Do not waste time by returning to the original polynomial. All right, so we have this new polynomial, x to the fourth plus whatever. Is it clear that it doesn't have any positive zeros? Think about synthetic division with c equals 0. We would get, at the bottom row, coefficients 1, 0, 7, 18, 10, which are already positive, or at least they're not negative. Anything to the right of c equals 0 would only make these numbers bigger. So we now know to try only negative numbers here. At this point, since no positive numbers should give a 0, and since this polynomial here has constant term 10 and leading coefficient 1, the test set of possible rational roots has shrunk considerably to just minus 10, minus 5, minus 2, and minus 1. This is a great improvement. All right, so we've factored this polynomial just a little bit, still have a fourth degree polynomial. We know there aren't any positive roots to try, so let's try a negative root. Let's try minus 1. If we divide by x plus 1 using synthetic division, we get this, and if we look at the lower right, we'll see the remainder is 2, so we found another factor. Minus 1 is a 0, so x plus 1 is a factor. This fourth degree polynomial factors into x plus 1 times a cubic that has coefficients 1, minus 1, 8, and 10. And so that fifth degree polynomial factors into 2x minus 3 times x plus 1 times its cubic. All right, now we need to factor the cubic, and there are no more positive roots to find, so let's try something like minus 2. If I plug in minus 2, in other words, I'm dividing by x plus 2, there's my synthetic division. Look at the number at the bottom right, that minus 18. Darn, it's not a 0. F of minus 2 is minus 18, and so minus 2 is not a 0. However, notice the pattern across the bottom row this time. When we plugged in a negative number. The pattern alternates. It has a positive 1, then a negative 3, then a positive 14, then a negative 18. If we were to try a more negative number like minus 5 or minus 10, it would only make the negative 3 more negative because we would be getting a middle row in which we're always multiplying by this negative. So the middle row would get larger in absolute value. So the negative 3 would be more negative. That would mean that instead of a 6, we'd have a more positive number than 6. So we get something larger than positive 14. Then we multiply that by a very negative number. We get something even more negative than negative 28. So the next step at the bottom, we'd have an answer that's more negative than this negative 18. At each stage in this computation, our numbers will be getting further and further from 0 than they already are. To illustrate this, let's try plugging in minus 3 or minus 4 into this polynomial using synthetic division. Notice how the numbers continue to alternate. 1, minus 4, 20, minus 50. or 1, minus 5, 28, minus 102, as the numbers get more negative, the bottom row gets larger in absolute value, alternating between positive and negative numbers. So x equals minus 2 is a lower bound for our possible roots. There's no reason to try anything smaller. Let's summarize what we've learned here. A lower bound for the zeros on a polynomial, if upon doing synthetic division with a negative value c, here we did minus 2 for example, the bottom row in our computation consists of numbers alternating in sign, plus, minus, and so on, then that c is a lower bound for the zeros. We don't need to look for zeros further along the real line to the left of c. For the purposes of this result, we'll always treat 0 as positive or negative, giving it whatever sign we wish to make it convenient for us. Alright, back to our factoring problem. We've factored this fifth degree polynomial into two linear terms and a cubic. And there aren't any more positive roots to find, and we know that minus 2 is the lower bound on the roots. We've now ruled out everything else in our test set, while discovering 3 halves and minus 1 is zeros. Now what do we do? Well, if you go back to this cubic, notice that when you plug in a 0, you get a positive 10. But a cubic polynomial has end behavior where it drops off rapidly to the left. So we know that although g of 0 is positive 10, eventually somewhere to the left of 0 the function becomes negative. So, by the intermediate value theorem, this cubic polynomial has a root which is negative, which we've not yet found. Did we try everything? Almost. We tried x equals minus 1 and found that it was a 0. And we agreed that minus 2 was a lower bound. What we did not do is test minus 1 again. It was already a 0, but we didn't test it twice. Recall that a polynomial can have a 0 with multiplicity 2 or more. So let's try minus 1, plugging it into this cubic. There's my synthetic division, and there on the lower right is a remainder of 0. So when I plug in minus 1, I get 0. So x equals minus 1 is a 0 of this cubic also. So it's a 0 a second time of this fifth degree polynomial. In other words, x plus 1 is a factor twice. So now I have this fifth degree polynomial, and I've discovered that it factors in the 2x minus 3 times x plus 1 times x plus 1 times this quadratic. Once we reach a quadratic polynomial, we're almost done. Factoring quadratics, remember, is easy. If I use the quadratic formula, then I ask, where is x squared minus 2x plus 10 equal to 0? There's my answer. It's when x is 2 plus 3i or 2 minus 3i. So the quadratic equation, x squared minus 2x plus 10, has two complex roots, appearing, of course, as conjugate pairs. So x squared minus 2x plus 10 factors into x minus one of those roots, 2 plus 3i, times x minus the other root, 2 minus 3i. So our final factoring of our fifth degree polynomial is that it factors into 2x minus 3 times that fourth degree, and then we discovered 2x minus 3 times x plus 1 times that cubic, and then we discovered further 2x minus 3 times x plus 1 squared times the quadratic, and then we factored the quadratic, so the fifth degree polynomial has linear terms 2x minus 3, x plus 1 twice, x minus 2 plus 3i, x minus 2 minus 3i. Here's the graph. Notice that x plus 1 is a factor twice, so minus 1 is a 0 twice, and then there's a 0 to the right at 3 halves. Let's summarize what we've learned about upper and lower bound for our set of zeros. If upon synthetic division with a positive value c, the bottom row is all positive numbers, then c is an upper bound for the zeros. We do not look further to the right of c. If upon synthetic division with a negative value of c, the bottom row consists of numbers alternating in sign, plus, minus, and so on, then c is a lower bound for the zeros of f of x. We should not look further to the left of c on the number line for zeros. In the next lecture, we look at Descartes' rule of signs.